Hi, everyone, and welcome back to Organic Chemistry on YouTube. Today we'll be talking about stereochemistry as applied to alkenes. These are compounds that contain double bonds or pi bonds, and this stereochemistry matters a lot in determining their structures, chemical and physical properties. So a little bit of introduction here to alkenes. So cis and trans labels correspond to the diastereomers between a cis and a trans stereoisomeric pair. Whether a molecule is cis or trans changes its physical and chemical properties. Remember also that you can't rotate around this carbon-carbon pi bond because the stabilization energy of a pi bond exceeds the amount of energy that would be required even when heating this compound to very high temperatures to allow it to rotate to be cis or trans. The only way to access a trans stereoisomer from a cis stereoisomer is to irradiate the compound with light. Let's do some examples. So this is an example of trans-2-butene. The way that I know that it's trans is by first assigning the stereochemistry based on a list of priorities. So just like in the RNS episode, we assign priorities based on the atomic number. And we're going to do it a little differently here with alkenes. You split the alkene in half mentally anyway. Now you look at the left side and you compare the carbon against the hydrogen. The one with the higher priority here is the carbon because its atomic number is 6, while the atomic number of hydrogen is 1. So since 6 is more than 1, carbon wins, and it gets the first priority, hydrogen gets the second. And then you forget about these two on the left, and you go move over to the right side of the molecule. Now here, we look at, again, the carbon versus the hydrogen. Carbon has the higher priority, has an atomic number of 6, while again, hydrogen has an atomic number of 1. And then you look at then the two sides. You can see that the 1 is opposite of the 1, so that gives it a trans configuration. If it were to be on the same side, like in the case of cis-2-butene, it would then be called cis. Here again, we compare carbon to hydrogen, and again, carbon to hydrogen. So on the left side, carbon gets a priority 1, hydrogen gets a priority 2. On the right side, hydrogen gets priority 2, carbon gets priority 1. Now you can definitely see that the 1s are on the same side of the alkene, and that's what makes it cis. Here's another example. Again, we split the alkene mentally here. We look on the left, fluorine versus chlorine. Chlorine gets the higher priority, has an atomic number of 17, whereas fluorine has an atomic number of 9. So fluorine gets the lower priority. Now comparing carbon to bromine, bromine gets the higher priority. Oops. And carbon gets the lower priority. Now you can see again, the 1s are on the opposite sides of the molecule, and as a result, this is a trans alkene. Okay, and one final example you might see, assigning the cis-trans stereochemistry here, again, we do the familiar thing. If on the left, chlorine getting the higher priority over hydrogen, 17 versus 1 for the atomic numbers respectively. But if we look on the right, fluorine is of course the same as fluorine, so they both have the same atomic number. So this molecule has no stereochemistry. This has no cis or trans label. I suppose this last example is somewhat of an exception, but maybe things you might ask in office hour are: 1, how do I describe the stereochemistry of a cyclic alkene? That one's a little complicated, and well, not enough time can be dedicated in a 5-minute or less video. And 2, what are the biological implications of cis versus trans isomerism? If there's a trans alkene, does it have the same biological activity as a trans alkene? Just some things to think about. With that, that's been Organic Chemistry in 5 minutes or less.